So there is this particular question of which I'm not really going to deep into. That an atom has a curve and an outside core, eh? And electron occupies an orbital for which the principal quantum number n is 4. The principal quantum number n is 4. The azimuthal L is 0, and the magnetic quantum number is 0, and the spin is positive a half and negative a half. Then the question is the atom is likely to be A boron, B sodium, C potassium, and D fluorine. So we are given this, what do I call it, the principal quantum number, the four quantum numbers of a particular electron. So the principal quantum number, the azimuthal quantum number, the magnetic quantum number, and the spin are given. And the question now is the atom, the element that will have an electron that will have all this, then it's likely to be what? So actually we can tell from the option given that for a quantum number of n, it means the electron occupies the fourth shell because this is the outer core given. So if n, the principal quantum number, because a principal quantum number corresponds to the shells, it corresponds to the shells, the first shell, that is the K shell, the L shell, the M shell, and the N shell of the of an atom. So this very particular atom having a quantum number of 4 means you have 4 shells. And from the options given, from the options given, from the options given, you have boron. Boron, as we know, has atomic number of 4. Is it 5 or 4? Hydrogen, helium, lithium, beryllium, boron. Yeah, 5. So the configuration would have been 2, 3. You understand? So where the quantum number here is 1, then 2. So the highest quantum number is 3. As for sodium, sodium has atomic number of 11. Its configuration will be what? 2, 8, 1. So the quantum numbers, the highest is 3. That is first share, second share, third share. Then where am I? We have potassium. We have potassium, which has 19 atomic number, so which will be 2, 8, 8, 1. Yeah, corresponding to the quantum number. So we'll come back to that. That is likely the answer. Then the option D, fluorine, which has atomic number of 9, giving 2, 7, corresponding to N1 and 2. So from here now we can tell right from with the quantum number that the atom or the element is likely potassium because that is the element that has up to 4 shells, up to 4 number of shells, where you can have the electron that actually has the whole of these properties. So all this other one describes the number, the azimuthal number of that particular electron, the magnetic quantum number of that electron is 0, and then the spin. So with all this, you can locate an electron. If you want to locate an electron, so all this information will enable you to locate them. Maybe subsequently, if you come across a similar question, then you will go straight further on these quantum numbers. But just get to know that as per this question, this is enough information for us to get the atom. for an electron in any orbital, in some of the orbitals could have the same properties of L, M, and S. Understand? So this is spinning, telling you the direction, whether electron spins upward or spins downwards, spins positively or spins in the positive direction or the negative uh, direction. So with this, we can say option C, which is potassium, is the answer. So this is likely where we are going to stop. I want us to treat up to question 10, but maybe we don't have time, or maybe we can still look at question 8. Let's see, because I actually want to explain the theory behind every question so that when we come across similar questions, we can answer them. I think the one we just solved is question 7. Then question 8. Question 8 says an element B has two isotopes. An element B has two isotopes, B20, B10, and B22, B10. Present in the ratio 2 to 3. And the question is, the relative atomic mass of B is the relative atomic mass of B is, that is the question. So you should all understand what isotopes are. Isotopes are atoms of the same elements, two or more atoms of the same elements, having different atomic masses. Of course, they will have the same atomic number. So when you write an element S, the atomic number is stated here, and the atomic mass is stated here. So A represents the atomic mass or the mass number. Z represents the atomic number. This is the atomic number. This is the atomic mass, or what some people will call a mass number. So when you have two or more atoms of the same element, so as far as they are the same element, they are going to have the same atomic number. So, but the difference is in their mass numbers or in their atomic masses. And we say the atoms are isotopes of each other. So we are given this. B does not represent a boron, it's just an arbitrary letter to represent the element. If I to go by the atom that has atomic number of 10, it should be neon and not B. But the name is not important here. We just use B as an arbitrary letter to represent that element. Then this is the isotope, and this is the ratio in which they are present, because their percentage about this isotope may occur in different ratio of abundance. That is to say that if you have 100 total of 100% by mass of this mixture, and you are told 2 to 3%, the ratio is 2 to 3. The ratio of boron 20 is 2 to 3 of boron 22. So that is to say that 2/5 of every 100 is boron. So in this case, this 100 or 200 by 5, so which means 40%. In terms of percentage, 40% for instance is boron 20. Then definitely the 60% will be for boron 22, which means boron 22 is more abundant than boron 20. So the question says you should find the relative atomic mass of B. So what is about relative atomic masses? Every atom has its atomic mass, but because of the existence of isotopy, there are some atoms will actually have isotopes with different atomic masses. It means we cannot pick one of the masses as the atomic number for the element. So just for instance, we can't say 20 is the atomic mass of element B. When we know that we still have other isotopes of the same element having different, we might still have other, maybe another one even having 24, 23. So why should you then pick one as the atomic mass? So instead, we use what we call relative atomic masses. Is a value as an atomic mass, like the average atomic mass that takes into consideration the abundance of all the isotopes put together. So the proportion, the percentage composition of each of the isotopes listed. So if that is the case, then we can use this ratio to determine the relative atomic masses. So what we do is, as for this, you can say we have 2 over 5. The total ratio is what? 5. So 2 over 5 of the mixture is what? Is boron 20. You understand? So 2 all over 5 multiplied by 20 is the contribution from from uh, from boron 20. Then plus 3 over 5 of 22 is the contribution of boron 22 to the relative atomic mass. So if we go by this, it means 40 by 5. I think that will give us 8. 5 here is 4. Multiplied by 2, 8. Okay. Then this should give us, this is 22 times 3 by 5. This gives us 13.2. The total now will give us was 13.2 plus 8. It gives us 21.2. So which means the relative atomic mass is 21.2. Let's see if that is found in the option. Yeah, we have 21.2 as option B. So you can see this, rather than 20 or 22, is the relative atomic mass of the element B. As simple as this. So another way we could have done it is set this 2 multiplied by 20, then plus 3 multiplied by 22. Then everything by 5 is still the same thing. I think it is better, it's more explicitly expressed in this form. So that is that about number, is that number 8 or 9? I don't really want to make the video bulky. Okay, like number 9 question. It's a question on electrolysis. Very interesting. We have already seen question 1 was on electrolysis. So question 2 is another aspect, question 9 is another aspect of the calculation from electrolysis, which we should look at. But let me check the time and see if that can be talked. Okay, so let's see if we can do it within 5 minutes. Question 9. So I read the question. So the quantity of electricity is required to deposit, or the quantity of electricity required to deposit 2.4 gram of copper in a period of, the quantity of electricity, I'll be shortening things, required to deposit 2.4 gram of copper in a period of 70 seconds, in a period of 750 seconds during an electrolysis or during an electrolytic deposition process is, so with other noise there, eh, is, so actually there is in between, before is there is during electrolytic deposition. Of course, during the electrolysis there are going to be deposition. So the question is asking us to find the quantity of electricity to deposit 2.4 gram of this. So the solution, like what you already understood here, to determine the quantity of electricity to deposit 2.4 gram of copper. Eh? So to deposit 2.4 gram of copper, that is Cu, then what's in a time of 750 seconds, second is S. Understand? To deposit this mass of copper in 750 seconds, then what quantity of electricity is required? This is what the question is talking about. So remember, by Faraday's first law of electrolysis, we stated that mass is proportional to quantity of electricity. And then we went further to say that quantity of electricity is the current multiplied by time. So if this is the case, we have to find the Q. The current we don't know, the time we know. So the question now is, how do we find the current? Then the information given to us is just the mass and the time. Then how do we go about this very question? How do we go about it? Using the mass and the second. So for us to deposit copper, then it is done at the cathode, where the copper takes up 2 electrons to deposit 1 mole of copper. The latent atomic mass of copper is usually 64, 63.5. Let me see if that is stated in the question. Yes, you say copper is equal to 64 for the question. Copper, latent atomic mass of copper is 64. And they tell you 1 Faraday, already know, you know, it should be 96500. Let's see what the question states. 1 Faraday is 96500 coulomb. It's a coulomb per mole. So we know that somebody would have said that if M is equals to, if we rewrite this and transform this into equalities, I would have needed a constant K. A constant K. So if this is to be substituted here, understand? In place of Q, we could have said Q is equal to M over K. So that on substituting for, what are we substituting for? So supposing K, what do I call it? K is known. So we could have simply gotten our K, but K is not known. So just take note of this. But this is how we are going to actually solve the question. This is what we are going to do. So we know the mass, then we know the current. So what we are going to do to determine K is this. From here we can see that 2 moles of electrons are involved, and this implies 2 Faradays of what? Electricity. It implies 2 Faradays of electricity to form 1 mole. That is to deposit 1 mole of copper. So, and 1 mole of copper has a mass equal to 64 grams. That is 1 mole or 64 grams of copper. So this is the quantity of electricity we need 2 Faraday to deposit 64 gram. So we come back here and say 2 Faraday is required to deposit 64 gram. We're working in mass because we have an information on mass. So if 2 Faraday will deposit 1 mole, which is equal to 64 gram of copper, then how many Faradays will deposit 2.4 gram of copper? So as usual, if you do our cross multiplication, this multiplied by this, because of this, then at the end of the day, our answer is going to be 2 multiplied by 2.4 divided by 64. And this will give us 2.4 times 2 by 64 to give us 0.075, 0.075. So what does that mean? So what does this mean? This implies that 0.075 Faraday gives 2.4 is the quantity of electricity that gives 2.4 gram of copper. So what we now need to do is to convert, because the quantity, to find the quantity, and the quantity should be expressed in coulomb. Q is expressed in coulomb rather than Faraday. So which means this value, you just convert this value to coulomb. So which is what? 0.075 multiplied by 96500. Because we know 1 Faraday is equals to 96500 coulomb. So if we do that, then we're going to have 0.075 multiplied by 96500. So we're going to have 7237.5 coulomb, and that should be the answer. So you can see that there was not even any need for the second, this 750 second given. We don't really, it is not necessary that every information supplied in the question must be used in the calculation. So this is just for information that the 2.4 gram was deposited. We have currents running for 750 seconds. So that does not necessarily mean we are going to use it. Let's see what answers we have here. Okay. The question is what quantity of current? Because the answers we have here are in ampere rather than in coulomb. You understand? So they are in ampere rather than what? In coulomb. So this is the quantity of electricity in coulomb. You understand? But the question I just saw is that, sorry, the question has appeared again. The question is saying the quantity of current, not of electricity, quantity of current. So if the quantity of current, it means we're actually looking for the current itself, not just Q. But before we can do that, then we need to know Q. So what we have gotten here is Q. This is the quantity of electricity required, 7237.5 coulomb. So having gotten that, then it will now be very easy for us to calculate for current using the formula Q equals IT. So this is where the formula now comes in. So we've gotten Q, then our I will be what? Q over T. So, and this will be Q already got it to be 7237.5 all over. The time was what? 750 seconds. Sorry, I forgot it. 750 seconds. So this should go out by 750. That will give 9.65 ampere, 5.65. So the current, the quantity of current required is 9.65 ampere. And let's see if we have that in the option. And that is option A. Correct. So first thought we are looking for the quantity of electricity Q. So of which this would have given us the answer. But they actually want the current. So having gotten this, we have to go further by dividing it by 750. So you can see how we made use of the first Faraday first law to get the or this very equation to solve our problem. But to find the current, so this equation would have given us the current. But the current is to get the current from here, we need the quantity of electricity. Time is given. You understand? So, but we don't know the Q. So then we now have to use the half equation, that copper 2 plus 8 plus 2 electron going to copper to know how much of electricity will give 1 mole of copper. So we saw that 2 moles of electron, which is 2 Faraday, in terms of charge, it will be 2,96500. We give 1 mole of copper, which is 64, has a mass of 64 grams. So if we know that 2F will give us 64 grams, then how many F will give us 2.4 gram in the equation? So then we are able to get that, okay, we need 0.075 F to get 2.4. Then what is this 0.75 F in column? Because we'll be needing Q, not F. So we now multiply it by 1 Faraday, which is 965 to get the quantity Q. And now recalling this equation, we can now divide this by the given time to get the current. I think that is all that was done. Then, so to make it 10, then we're able to call everything. This question 10 is just, it's nothing to write. It's about still another electricity, I think electronics. It's a platinum electrodes are dipped into copper sulfate solution in a voltameter. The solution left after electrolysis is A clear, B blue, C pale blue, D sky blue. So how do you answer that? Okay, let's quickly see if we can do that. I really don't like making video bulky, that's why any question that requires much explanation, I give a separate video for that. Okay, but let's see. The platinum electrodes are dipped into copper 2 sulfate solution. You have a copper 2 sulfate solution here. Then platinum electrodes are dipped. Of course, you have your connections. This is the electrolyte. So the electrolyte is copper 2 sulfate solution. Then the question simply is that after the electrolysis, the solution that will be left, the residual solution is what? What will be the nature of the color? Actually, starting with copper 2 sulfate solution, I think the color, the original color of this solution, I think is deep. Is deep blue. This is the original color. Now, what now happens to the color? From the question, the answer said deep, clear, pale. So let's see what happens to the color after the electrolysis. So simply put, for them to have specified platinum electrode, it means in a copper sulfate solution, it means it's an inert electrode. So they are telling you that electrode will have no effect in the, or have no interference with the reaction here. So that is to say that when you have copper sulfate, will ionize to give copper 2 ion plus sulfate ion. Then being in a water solution, the water will ionize to give this plus this. So when that happens, so like I said, these two positive ions, which are the cations, they have to migrate to the cathode, and the two negative ions will have to migrate to the anode. So at the cathode, one of these has to be discharged. So if you are to follow the electrochemical series, like I told you, the lower will be discharged. In this case, copper is the lower because hydrogen comes before copper. So if copper is the lower, then that is copper 2 will be discharged according to this equation at the cathode. At the cathode. You understand? So copper is deposited. So this is to say that copper 2 ion is being removed from the solution and get deposited at solids on the cathode. So gradually as the reaction proceeds, we are removing copper out of the system. And what gives the blue coloration, the blue color to the copper surface originally is the presence of copper 2 ion. So as we are drawing copper 2 ion out of the solution, you should expect the blue color to disappear. Then this is what happened at the cathode. So if it were hydrogen that was being removed, they would have expected the color to remain same. So even at this point, we can give the answer. But let's see what happens at the anode. At the anode, we have sulfate ion and hydrogen ion. So anywhere you have these two, always 0H is discharged, even if this solution is concentrated. So from the chemical series, like the one I gave, so the lower, that is, if you have a chemical series that starts with fluorine and ends with hydroxyl ion, then the lower is 0LH, is below this. So we are going to discharge this. And if we discharge that already, we know the anodic half equation, the overall equation to be this. You understand? So here, oxygen gas is liberated, which is the product at the anode. Here at the cathode, we have copper being deposited. Now, if I to look at the residual solution, that is after this have taken place, then what is now the nature of the remaining solution in the system. So you can see that from here, most of the copper ions have been taken away, removed from the solution to form copper deposited as solid on the cathode. And from here, OH has been removed. So it now implies that in the residual solution, you're going to have um, hydrogen ions, which is unused, then plus the surface ions that were unused. So if they combine, being oppositely charged, so they will combine to form a kind of acid, H2SO4. You understand? Let's say if you have to balance it, to put you here. So the residual solution contains the undischarged hydrogen ion and undischarged sulfate ions, which will combine to form H2SO4. H2SO4 is an acid. So we can say that the residual solution is acidic, but that is not what we have in the option. The option is it's about the color change, not about the acidity or the alkalinity or the neutrality of the residual solution. A question might also come, and you could have also got the option of okay, acidic, basic, whatever. So because of the formation of H2SO4 in the residual solution, it means the residual solution is acidic. But in terms of color changes, then it the option that I will go for is that is what we call it, the pale blue, because the deep blue will be disappearing. If the reaction is complete, what we can say the answer is clear. Clear means we are going to lose all the blue coloration, that we will end up having a clear solution, a colorless solution, because that will happen if we are sure that all the copper 2 ions were removed or were converted to copper. But it may not be possible. We may not have 100% conversion of so the conversion what do I call it, level is not given. So but what we know is that the blue coloration is lost. It fades away. So if that is the case, that should be the best answer. And that should be option A, say clear, B, say blue, C, pale blue, D, say sky blue. So pale blue, from deep blue, we know if it fades, we are getting pale. So if it's not deep, it is pale. So the color becomes pale. Understand? You see the solution left after electrolysis. But if it's after complete electrolysis, it will go clear. So if all the coppers are removed. but electrolysis is hardly 100% converted. So in that case, we should have a pale blue. Now, is there any confusion? Whether it should be clear or pale blue? Because clear means at the end of the electrolysis, complete electrolysis, it should be clear because all the copper ion must have been removed. But when we say that if it is in the course of the electrolysis, in the course of the electrolysis, then it should be pale. So now which option do we go for? From deep blue to pale, then if electrolysis is completed, okay, since when they say at the end of electrolysis, then we are going to assume a complete electrolysis. Then we go for clear. The blue color must have all disappear because if there is no, if all the copper two ions are converted, then there will be nothing in the solution that will give the blue coloration again. What we have in the solution will just be the hydrogen ion and the sulfate ion, and they don't impact blue coloration. So we can say clear in this case. But if the question says in the course of the electrolysis, what is the nature of the solution? Then definitely it will be getting from deep to pale. So we will go for clear. So if you have your series, maybe with you where you have this question, I don't really have it, then you can check who they choose as the answer. Though somebody like me must have chosen the answer. So maybe based on what it says, it could choose something. But I know if the electrolysis is completed, is what we should have done here at the end of the electrolysis, it means we're going to have a clear solution. Thank you.